Okay, so I guess I'm going to go ahead and get started. Uh, so today we're going to cover the next section 6.3, and it's about what are called estimators, and I'll explain what those are in a moment. And what I'm going to do is I'm going to go through this pretty long example that has several parts to it to kind of explain what's going on with these estimators. And then this is going to bleed into what's called the central limit theorem. So after we kind of go through this example, we'll talk about the central limit theorem, which is really a topic in the next section, 6.4. So that's kind of where we're going to end today, is the very beginning of 6.4. And then next time we'll do some problems from 6.4 where we apply the central limit theorem. But kind of what we're doing today is we're laying sort of the foundation, like the theory behind some of the stuff that we're going to be working on um, later on in the course, including the next section. Okay. So I'm going to use this example to illustrate some of the ideas that we're going to be looking at. Okay, so first of all, let's suppose that you have a population of 3 houses, and we're going to look at how many people live in those houses. Now, there's two perspectives that I want you to be aware of that we're going to take when looking at this particular example. One perspective we're going to take is the perspective of someone that knows what the population looks like. I'm going to call that like the all-knowing perspective. So if you had the all-knowing perspective, let's just say, for to make things simple, that this particular neighborhood only has 3 houses in it. Okay, remember capital N stands for the population size. So the population here consists of 3 houses, and that's it. Okay, it's a very small population, but that's our population. And if you look at, we're going to look at the number of people that live in those houses. So if you look at all the houses in the neighborhood, there's only 3 of them. And in one house, I guess it's up for sale and nobody's currently living in it, so there's nobody living there. And then in the next house that we look at, there's 2 people living there. And then the third house we look at, there's 4 people that live there. Okay, so this is what the neighborhood looks like. That's it. There's only 3 houses, and these are the people that live in those houses, right? 0 in one house, 2 in another, 4 in another. Okay, and then we're going to define this random variable, x, right? We usually use x for random variable, be the number of people that live in a randomly selected house. So we're going to randomly pick one of these houses. You might put um, a piece of paper in a hat and just shake it up and pick out one of these numbers, 0, 2, or 4. Okay, and we randomly pick one of them. And X is going to be the number of people that live in the house that we randomly selected. So if we select the first house, then X would be 0, right? If we select the second one, then it's going to be 2. If we select the third one, then X would be 4. Okay. So there's only 3 possibilities for X, 0, 2, or 4. Okay. And now a couple of things we're going to do here. Okay. This population, we're going to look at, there's 3 things that we always like to know about our random variable. So we would like to figure out what the average is for the random variable. So I'm going to label that with the mu. Mu stands for the population mean, and I'm going to label it with a subscript, a sub x, just to clarify, just to be clear that it's the average of the x values, of these values here, these 0, 2, and 4. Okay. We haven't used this in the past with a subscript. We usually just call the population mean mu, but I'm going to put an x on it because we're going to talk about more than one random variable. So this is going to be the mean of the random variable for x, okay, or the random variable x. And then this is going to be the population standard deviation, right? Sigma is the population standard deviation, and I'm going to use that same notation with the subscript x, and that's going to be the standard deviation of this random variable x here. Okay. Okay, we're going to find both of those in a moment. Other thing we'd like to know about our random variable is how it's distributed. If you made a histogram, what would that look like? And that's where I'm going to start. So let's suppose, like I said, you put these 3 numbers in a hat, you shake it up, and you pick out one of the numbers. what's the probability that you would get a 0? That's one of the possibilities, right? Well, there's 3 houses and only one of them has a 0, so it should be 1 out of 3, right? A 1 in 3 chance you get a 0, a 1 in 3 chance you get a 2, and then a 1 in 3 chance you get a 3 because you're picking them randomly, right? And so what kind of distribution does X have here? Well, this is what we call a uniform distribution. The probability is the same for every possible outcome for the random variable. When it's the same, the probability is the same. It's called a uniform distribution. So if you made a histogram of these values, it would look something like this. So getting a 0 and a 2 or a 4 all have the same probability, 1/3. So there's our probability histogram. Remember, a probability histogram just tells you the probability of getting any particular X value here. So this just says that the probability of getting a 0 is 1/3, a 2 is 1/3, and a 4 is 1/3, which is exactly what this uh, table tells us. We're just putting it into a picture here, okay? Okay, so look, news. We know what the distribution looks like. If you randomly pick one of these houses, there's a 1 in 3 chance you would get any one of those numbers. So it's a uniform distribution. Okay, so then the next thing we'd like to know is what happens on average. So that's pretty easy to calculate. When you calculate a population mean, you just add up the total, add up all the numbers that you have in the population, and you divide by the total numbers, right? Which is 3. So all we have to do is add up these numbers, and then average them over the total, which is 3, and you get 6/3, and it's just 2. So on average, you're going to get a 2. That's what it averages to. So that's the population mean for this random variable. Okay. Then the other thing we like to know is how does it vary from the mean? How do these numbers vary? And obviously they vary some, right? You're not always going to get a 2. Now remember, if the standard deviation were 0 here, that would mean that we never vary from 2. And that would mean every number in our population is simply a 2. So it can't be 0, right? There is some variation from 2. We have a 0 and a 4. Okay. So there's a formula for calculating this that we talked about, I guess, in chapter 2. Um, In fact, there were 2 formulas that we talked about for standard deviation. One's for the sample, and there's another one for the population. The one we need to use here is the one for the population. And if you need to refresh your memory on what that looks like, you can go back and look at it, but I'm just going to do it on the calculator just to make it easier. There is a formula, right, that you can use to calculate population standard deviation. Now, if you do it on the calculator, go to the stat button, and then you go to edit. That'll pull up this menu here, and at edit, calculate, and test, just stay on the edit menu and select the first one, edit. And that's how you enter your data. And I've already got some data entered in here. I'm just going to go to L1 and I'm going to clear everything out. So you scroll up to L1 and you can press clear and scroll down. And then I'm going to put in the numbers I want, which is 0, 2, and 4. Now, I mean, I do have some data in L2 and L3, but you could leave it in there if you want. To be cleaner, I'm going to clear them out. We don't need those. Okay, so once you get your data into like L1, and you go back to stat, but this time you scroll over to calc to calculate. And then you get this menu here. It's got various things on it. We'll talk about some of these later on. One we're concerned about is at the very top, it's the one variable statistics. So you click on that, and then you got to click it on it again for you to get the information about your stuff that you put into L1 data. Okay, so you can see at the very top it says X with a bar on top. Normally that means sample mean. Calculator is kind of assuming that the data you put in is coming from a sample because typically it is. But in our case, the data that we put in actually is coming from a population. So it's not correctly labeled. They're labeling it as a sample mean, and it's actually a population mean. So, but that's our mu. That's our average. Okay, we already knew it was 2. It's 2. What I want is, now if you scroll down, you see at the bottom it says S sub x. Again, they're using the subscript x like I am. That's the sample standard deviation. So if this was a sample data, this would be the standard deviation. We have a population, so it's the sigma sub x, right? So that's our population standard deviation. And remember, the formulas are slightly different. So these numbers are, not the same because of that. So we want the bottom one, right? The 1.63. And I'm just going to round it off to 1.63. So that's our standard deviation because it's coming from a population and not a sample. If it was coming from a sample, our standard deviation would be 2. But again, it's coming from a population. So let's go back. It's 1.63, roughly. Let me just write that. That's rounded off. So that means approximately 1.63. Okay, so now we know everything we'd like to know about the random variable, right? We know how it's distributed. It's uniformly distributed. The average is 2, so it centers at 2. And then it deviates from 2 by about 1.63. That's our standard deviation for this population, okay? Now, why am I doing this? Because what's going to happen in future problems is we're going to tackle this a little differently, and we're going to work with a slightly different random variable. And so we need to talk about how that differs from this random variable, because there are differences between the two. So the next random variable that we're going to look at is, what we're going to do is we're going to take the perspective of a sampler. So let me go back. The first one, this is the all-knowing perspective. If you knew what the population looked like, and this was your random variable, then this would be the mean, the standard deviation, and distribution of that random variable. If you knew what the population looked like. Now we're going to take the perspective of the sampler. And to be quite honest, this is usually what happens. I mean, the reason you're taking a sample is because you don't have the time or the money to go investigate and look at the entire population. So this is the more realistic case. Like in the real world, most people don't know what the population looks like. And that's the reason they're taking a sample. So let's take the sampler's perspective now. This would be the all-knowing perspective, if you knew what the population looked like completely. Okay. Let's suppose that you don't know what the population looks like and you're going to sample. And what we're going to do is we're going to randomly pick 2 households from the population. Now look, the sampler doesn't even know how big the population is. Okay. If you go back to the previous screen, we know that it has 3 houses in it. But now that we have the perspective of the person sampling from the population, they don't even know how big the population is. The only thing they're going to know is, I'm going to pick 2 houses at random from this population, and I'm going to get the 2 numbers. I'm going to look at how many people live in those 2 houses, and I'm going to get those 2 numbers. That's pretty much all I'm going to know. Okay, I'm not going to go know anything else about the population. So what could happen, then what we're going to do is we're going to average up the number of people that live in those 2 randomly selected houses. Okay, so let's think about what could happen here. So you have a bag of 3 numbers in it. What was it? 0, 2, and 4. Sorry, 0, 2, and 4. Number of people that live in the 3 houses, right? Now you don't even know how many pieces of paper there are in the bag. You just randomly go in there and pick one out. Okay, so let's think about what might happen. Maybe I should write that down first. Okay, we're going to do this with replacement, what's called with replacement. down first. Okay, so look, here's my bag. I randomly pick one of the pieces of paper in the bag and I look at what it says. What could happen? All right, well, I could get a 0, 2, or 4. So let's start with 0. Look at the possible samples of size 2. With replacement. Okay, so I picked first one, right? I could get 0, 2, or 4. And I'm going to do this as organized as I can. So you could pick a 0 first. Then what I mean by with replacement is you put the number back in, the piece of paper back in the bag, you shake the bag up, and then you pick again. So if I replace the first number that I pick, then I could get that same number again, right? So I might get a 0 first, and then I might get a 0 again because I replaced it. So that's one possibility, right? Or I could pick a 0 first and then pick a 2, or 0 first and then a 4. So that takes care of what might happen if I pick a 0 first. And then now let's say I pick a 2 first. If I pick a 2 first, it's the same sort of pattern. I could pick a 0 next, or I could pick a 2 next, or I can pick a 4 next, right? And then lastly, I could pick a 4 first. And I'm running out of space, unfortunately. Then you also have a 0, pick a 0 second, a 2 second, and then a 4 second. Okay. So look, I've listed all the possible things that could happen when you sample 2 of these with replacement, right? You could get any one of these 9 samples. Now, the only reason I can write down the 9 possible samples is I'm actually taking the all-knowing perspective to be able to write down all 9 of them. So think about the difference here. The sampler is only going to sample the 2 numbers, and all they're going to know is the 2 numbers that they get. Okay. So the sampler, let's say, gets 0, 2. That's all they know. They don't even know a 4 is in there. All they know is that they got a 0 and they got a 2, and that's their sample. They don't even know that there's 9 possible samples, right? The only way that we know there are not these 9 possible samples is if we take the all-knowing perspective, and we know that the only 3 numbers in the bag are 0, 2, and 4. So we've got 2 perspectives here again. All-knowing perspective allows us to write down the 9 possible samples of size 2. The sampler is only going to know 2 numbers they get in their sample. They're going to get one of the numbers, and that's all they're going to know. Okay, so just keep that in mind. So let's suppose, let's go through and see what they would think the sample mean is. Okay, so if they got 0, 0, sample mean would be 0, right? If they got 0, 2, if the sampler got 0, 2, that would average up to 1, right? Sample mean. 0 and 4, again, I'm just doing this average, right? So 0 plus 4 divided by 2 would be 2. Okay. This one would be 1, right? 2 plus 0 divided by 2 is 1. That would average to 2. This would average to 3. 4 and 0 would average to 2. 4 and 2 would average to 3. And then 4 and 4 would average to 4. Now, reason one of the reasons the sampler's doing this is to come up with an idea of what trying to estimate what the population mean is. So let's pretend you're the sampler. You're trying to get an idea of what the average number of the mean number of people that live in the houses in this population looks like. What's the average number? What they're going to do is they're going to randomly pick 2 houses, look at how many people live in those houses. So they might get 2 and then 4. And then they're going to say, okay, my best guess as to what the average is whatever the sample mean is. And the sample mean in that case would be 3. That's an estimator. They're estimating, they would use that to estimate the population mean. Now, what's the actual average? What's the real population average? It is, remember, average is 2. Okay. So the sampler doesn't know this, right? Because they don't know the entire population. So what they're doing is they're sampling two at a time and looking at the sample mean to estimate the population mean. And so what could happen? They could get 0, 0, and then the sample mean would be 0, and that would be their estimate for the population mean. Of course, that's underestimating actual answer. The actual answer is 2, right? Or they could get a 4 and a 4, and their sample mean would be 4, and then they're overestimating the population mean, which is 2. Sometimes they get the correct answer, right? If they got a 0 and a 4, the sample mean would be 2, and that's their estimate for the population mean, and it actually is 2. So this is called an estimator. X bar is an estimator for the population mean. And what we want to do here is to evaluate whether it's a good estimator or not, and something that makes it a good estimator. What makes it a good estimator is not that it gets the correct number every time, because obviously it's an estimator, right? So an estimate doesn't have to be perfect. That's why it's called an estimate. But what we do demand of an estimator in order to call it a good estimator is that on average, it's targeting the correct answer. So the correct answer here is 2. Let's see what happens on average, because these are the 9 possible sample means that you could get and use them to estimate the population mean. Sometimes you're underestimating, like when you get a 0, and sometimes you're overestimating when you get a 4. What we want to know is what happens on average. So what I'm going to do is add up these numbers, average them up over 9 possible samples, and see what it averages to. So I'm going to call this the mean of the sample means. So it sounds kind of crazy to use the word mean twice in this sentence, but it makes sense. The mean is just the average, right? So I'm just saying the average of these sample means, and these are called sample means. So I'm finding the mean of the sample means, the average of these sample means, right? All right, so let's just add those up. I'm just adding these numbers up. Let me make sure I have all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you divide by 9, right? To average it out. And you can see this is going to add up to 18 over 2. Yes. All right, 18 over 9, right? Which is 2. Right. So look, news here. The numbers that the sampler would use, using to estimate the population mean, sample mean, don't always get the correct answer, right? I mean, like I said, they might get 0, 1, 2, 3, or 4. The only time they're correct is when they get a 2. On average, targeting the correct answer, right? If you average these up, it averages to 2, which is exactly what the population mean is, right? If you go back. So we would call this a good estimator. That's how we know whether it's a good estimator or not. It's called an unbiased estimator. So we can conclude that X bar is an unbiased estimator for our population mean, which I'm calling mu sub x. So you can use this to estimate population mean and be confident that not you're getting the correct answer, like 1, 0, 0, 1, 2, 3, 4 is the correct answer, but on average, you're confident that it's giving you the correct answer as an average. That's what makes this unbiased. Unbiased estimator. I left the word estimator off. And so this is what happens in the real world. If you don't know what the population looks like, it's too big, it's too costly to get to everybody, then you take a sample, random sample, because you don't want to favor any particular group. So you make it a random sample, and then you look at, and you might get one of these 9 samples. You don't even know that there's 9 possible samples. All you know is you get say you get the sample right here. You're going to average up sample, it averages to 1, and you're going to say that's my best estimate for the population mean. Now, the actual population mean happens to be 2, so you're underestimating it. But on average, this is going to give you target the correct answer of 2. Okay, and that's what makes it an unbiased estimator. Okay, everybody okay with this so far? Okay, if you have any questions, just let me know, right? You can send me a chat message or you can unmute yourself, okay? Okay, so that's kind of the first part of this. What we're going to be looking at is not just estimating the population mean, but also other things about the population. We might want to estimate the population standard deviation. And then we're going to look at, some of the other problems in my math lab will ask you to determine whether this is an unbiased estimator or not. Okay, we'll talk about that in a second. But this is not the only thing we're going to estimate about the population. There's more that we would want to estimate besides the population mean. Okay, the other thing I want to look at here is the distribution. All right, so here's my random variable, right? Here's my second random variable. This one is the average number of people that live in 2 randomly selected houses. Notice that's different than the original one, which we selected only 1 house, right? Notice the difference between 2 random variables. This one, x, is just the number of people that live in that 1 house that we selected. This random variable, the one down here that comes from the sample, has a bar on top of it, x bar, that's the random variable. And the reason we put a bar on it is because it's an average, it's a mean. It's the mean number of people that live in the 2 houses that we randomly select from the population. So the big difference between the first random variable and the second one is the first one, we're selecting only 1 house and we're recording how many people live in that house, and that's called x. And the second one, we're picking 2 houses and we're averaging up the number of people that live in those 2 houses, and that's x bar. That's our random variable x bar, whatever that number is, and the possibilities for x bar are listed here. There's these possible 9 outcomes for x bar. And now what I want to do is create a probability table for these possible outcomes. I mean, so what could x bar be? It could be 0, 1, 2, 3, or 4. Now we're going to look at what's the probability that you get any one of these particular outcomes. Okay, so let's start with 0. There's only 1 0 that you could, there's only 1 0 here, right? Out of 9. So there should be a 1 in 9 chance of getting a 0. What about 1? X bar could be two ways, right? It could be a 0, 2 or 2, 0, and that would average to 1. There's 2 ways that can happen, so that's 2 out of 9. 2 out of 9 chance. All right, 2. There's 1, 2, 3 2s, so that's 3 out of 9. 3. There's 2 3s, so that's 2 out of 9. And then 4, there's only 1 4, so that's 1 out of 9. Okay, I'm going to go ahead and erase some of this so I can put this, I'm going to put this into a histogram so we can get a picture of it. Oh, by the way, we just found, so I shouldn't have erased this, but the number that we found over here, right, the 18 over 9, the mean of the sample means. We don't want to keep writing this, this math. We don't like to write out these huge sentences. We like to come up with symbols for this so we don't have to keep writing down all these words. So the way we're going to notate this, mean of the sample means, is now you have to look at this. This is a population right here. Don't get confused here. This is a sample. 00 is a sample. 02 is a sample. 04 is a sample, right? Each of these are samples of size 2. But if you look at all the possible X bar values that come from these samples, we have listed all possible X bar values that could come from samples of size 2. So this, if you list all the numbers here, these are all the possible X bar values. So you can think of this as the population of X bar values. That's the entire list. And we just averaged them up. So when you average them, when you have a population mean, we use the symbol mu, right? This is a population of 9 numbers. We have all of them. So we're going to use mu to denote the mean of them. So the way we're going to symbolize this or notate this mean of the sample means is it's a population mean, right? This is a population of 9 numbers, and we averaged them up, but it's the average of the random variable X bar, not X. So I'm going to use a subscript X bar here. Okay, so this is going to be the mean of the sample means. Once you kind of see what's going on with this notation, it makes perfect sense. Both population means, so we're using mu for both of them. This one is the population mean of the X bar values. That's why we use the subscript X bar. So if you average up all the X bar values in the population, this is what they average to, right? They average to 2. If you go back to the other random variable, we put a subscript X on it. Now this is still a population, right? This is a population of only 3 numbers. And the average of those 3 numbers averages to 2. So we still use mu for the population mean, and we just put a subscript X just to make it clear that we're averaging up X values here, not the X bar values. Okay, now getting back to this probability distribution, we now know the probability of getting any one of these X bar values. Okay, in fact, let me write it down again because it's hard to see, but it's 1 out of 9, 2 out of 9, 3 out of 9, 2 out of 9, 1 out of 9. Okay. Now I'm going to put this into a histogram. This is just a probability table, but we like to put probability tables into probability histograms just to get a picture of it. So if you put X bar down here and the probability on the y-axis, the first thing is 0, and that has a probability of 1 in 9. So I'm just going to make a little box here and say that's got a probability of 1 in 9. Okay. All right. 1 has a probability of 2 in 9. So that's 2 out of 9. And then 2 is the highest probability at 3 out of 9. And then notice it goes back to 2 out of 9. So 3 has a 2 in 9 probability. And then 4 goes back to 1 out of 9. And so what kind of shape does our histogram have? Bell-shaped. Right? This is what we call bell-shaped. This is a perfect bell-shaped distribution. It's symmetric about the center. It goes from 1 out of 9 to 2 out of 9 to 3 out of 9. It peaks there. That's the peak of the bell. And then it goes back to 2 out of 9, just like it was over here, and then back to 1 out of 9 over here. This is a perfectly bell-shaped distribution. So the distribution of X bar is bell-shaped or normal. Okay, so a couple things to note here. You go back and look at the original random variable when we only took one house at a time. Its distribution was uniform, and it averaged to 2, right? You look at the new random variable, the X bar one that we're talking about on this other page, this random variable where we're averaging up number of people in two randomly selected houses, distribution of this is now starting to look bell-shaped. In fact, it's perfectly bell-shaped. So the distribution has changed. It started off as uniform, and then when we start averaging two at a time, instead of taking one at a time, when we start averaging two at a time, we start to get a different distribution. It's bell-shaped. So that's important to take a note of. Other thing to take note of is the mean has not changed. The average, the mean of x bar, the x bar random variable is 2, just like it was for the average of the x random variable, which was also 2. So the average has not changed. What is that telling us? If you try to balance this, it would balance at 2. That's the middle. And if you look at the other one, the shape has changed. If you try to balance this little thing, it would still balance at 2, right? Because it's the weights distributed symmetrically, evenly, right? So this would still balance at 2, despite the fact that it has a different distribution. What's different about the 2? Everything is getting bunched up towards the middle here at 2. So one of the things you have to draw from this is when we start looking at samples, okay? Now remember, the first random variable is we just pick one household and we count up how many people in that are in that household. We're not averaging up anything. We're just counting how many people are in that particular household. So X is not an average. It's simply the number of people that live in the household that we picked. Whereas the second random variable, we're doing something fundamentally different. We're selecting two households at random for our sample, and then we're averaging them, the number of people in those households. So now X bar stands for an average, mean, right? It's the average number of people that live in the two houses that we selected. And once you start doing something like that, where you're averaging up the numbers from your sample to get your sample mean, the X bar values here begin to take on a bell-shaped distribution, regardless of what the original distribution looked like. Doesn't matter what this distribution looks like. You're going to start averaging up numbers in your sample and looking at X bar, and distribution of X bar will start to look bell-shaped. Okay, so that's one thing to note. But the mean will not change. Average of the X bar values is the same as the average as if you were taking one at a time, average for X. And the last thing I want to look at is what happened to the standard deviation of these X bar values when we started averaging them up. How does that compare to taking only one number at a time? And look at what's the standard deviation for the X random variable versus the X bar random variable. Now in the original one, when we took one at a time, it was 1.63. I would argue, just based on looking at the picture, that there's more variation going on here. 0 happens 1/3 of the time, and 0 is 2 units away from the center. 4 happens 1/3 of the time. It's also 2 units away from the center. Compare that to what's happening down here. 0 happens, but it only happens 1/9 of the time. So it happens less often. It's still 2 away. It only happens 1 out of 9 times. It doesn't happen 1 out of 3 times. So I think there's less variation here, right? 1 happens 2 out of 9 times. If you add these together, it's 1/3 of the time. The other diagram was 0 1/3 of the time. In this diagram, 1/9 of the time it's 0, and then the other 2/9 of the time it's only a 1, which is closer to 2. So I think just by looking at the diagram, you can tell that there's less deviation in the numbers here, closer to 2. Okay. And so let's figure out what it is exactly. And the way you would do that is, again, we just go to the calculator, and I'm going to go to stat, edit. This time, I'm trying to find the standard deviation of the X bar values, the population of X bar values. Now remember, I'm talking about all 9 of them. This is the population of the X bar values. So I've got to put all 9 of these into the calculator to find out what the standard deviation is in these 9 numbers. That will give me the standard deviation in X bar. Okay, so let's do that. So go to stat, edit, and now put in, all right, so it's 0, 1, 2, and then it jumped back to, let me pull it back up, see what it was. 0, 1, 2, 1, sorry, 0, 1, 2, 1. And then it goes 2, 3, 2. And then it goes 3, 4. Okay, so that's what our, that's the list of X bar values. Okay. And now I'm going to go to stat, and then I'm going to calculate, again, one variable statistics. And you can see the average of those numbers is still 2. So that's my mu sub X bar. And then if I scroll down, this is a population of all 9 X bar values. So again, we're going to use sigma sub, it should be X bar, okay? Sigma sub X bar is 1.15. Roughly, okay? So I'm going to go back to that. This is approximately 1.15. And so notice that the standard deviation indeed did go down as we expected, because before it was 1.63, right? Now it's a little bit less. And you can see that in the picture. There's less deviation from 2. Now, and in fact, this number actually there's a relationship between this number and the original standard deviation. It's actually the original standard deviation, which we're labeling as sigma sub x, divided by the square root of the sample size. And I'll prove this to you. This is always true. Original sigma sub x bar was 1.63, right, if you round it off. And then we're sampling 2 at a time, right? Our sample size consists of 2. So if you take 1.63, which remember is the original standard deviation for x, right, here, for this random variable. If you take that number and you divide it by the square root of the sample size that you're taking over here to get your X bar values, that will give you the standard deviation and the X bar values that you have here. In other words, sigma sub X bar. Okay, and let's just see if that's the same as 1.15. Just to double check it. So it's actually easier to do it this way, right? Rather than put all the 9 numbers into our list and then going to one variable statistics, we could have just done this. We could have just taken our original standard deviation of 1.63 and divided it by the square root of the sample size, which was 2. And indeed, we get the same number, 1.15. Okay, so let's take a step back, and I'm going to, all this information, we're going to condense down into a theorem called the central limit theorem. And then we'll be done for today. And then we'll pick up with the central limit theorem. We'll actually apply the central limit theorem when we get to 6.4. Okay, so here's what the theorem says. It's probably the most important theorem in statistics. It says the central limit theorem says for all samples of the same size n. Well, for my example, n is 2, right? So for all samples of the same size n, for us that was 2, and it says within greater than 30. Well, we didn't go above 30. Okay, so let's say, you went above 30, then the theorem says, so I sampled 31 houses at a time, okay, instead of two. It says for all samples of the same size, n, where n is above 30, the sampling distribution of x bar, so they use this fancy word sampling distribution. Just think of that as the distribution that you get for x bar after you've sampled 31 at a time. The distribution of x bar can be approximated by a normal distribution. Well, isn't that exactly what we just saw in our example? I did it with only two, right? I sampled two at a time, and we looked at the distribution of x bar. They call it the sampling distribution, but essentially, when they say the sampling distribution of x bar, they're talking about this distribution here. So I sampled two at a time, looked at the possible values of x bar. How are they distributed? That's called the sampling distribution. It's coming from these samples. The sampling distribution of x bar, how does it look? Well, it began to look bell-shaped. That's how it looked, right? And what the theorem says is if you're above 30 your sample size, well, we were only at 2, but it says if you're above 30, we're confident in saying that the distribution of x bar will start to look bell-shaped. Now, in the example I did, I only sampled 2 at a time, and it was perfectly bell-shaped. But that's just because I picked numbers in the population which would make it look bell-shaped, so you could see this. So as a rule of thumb, regardless of what your original population would look like, the X distribution, as long as you're picking samples of more than 30, then the theorem tells us that the distribution of X bar will start to look bell-shaped. It'll be approximately normal. And what will the average be? We'll have a mean of mu. Okay, they're using mu. They should label this with a sub x. Okay, label that with a sub x. The average will be the same. Look at it. What was the average of these x bar values? It was, we labeled it mu sub x bar. It was 18 out of 9, so it was 2. This turned out to be exactly the same as mu sub x. And they're calling that mu. They're not putting the x on it. So they're calling this mu instead of mu sub x. So isn't that what happened? We averaged up the x bar values that we had here, and we found mu sub x bar to be 2, and that was exactly the same as the original, the population mean of the x values, which they're calling mu. So that's what this is saying. The sampling distribution of the x bar values are approximately normally distributed, with the mean equal to mu sub x, or mu. And what did the standard deviation look like for the x bar values? Well, it was sigma divided by the square root of n, and this should be sigma sub x, right? They're using, so going back to my thing, they're calling this sigma instead of sigma sub x. So what's the standard deviation of the x bar values? Oh, it's sigma sub x, or sigma, whatever you want to call it, divided by the square root of n. We're calling this sigma instead of sigma sub x. That's what that says. So look, here's what the central limit theorem tells us. When you sample, that's what we do in the real world. When you sample from a population, if you're taking more than 30 people in your sample and you're averaging them up, what will the X bar values look like if you create a histogram? They will start to look bell-shaped. That's what it says. Big important idea. What will the average of those X bar values be? Well, they'll be the same as the average of the X values that the population consists of. The mean is not going to change. It'll be the same. But the standard deviation of the X bar values is going to go down because everything is getting scrunched towards the middle. That's the reason this is happening. If there's one thing you want to catch from this, why is this happening? Why is the standard deviation going down for the X bar values? Think about it. In order to get a 0 for X bar here, I would have to get 2 zeros in a row because I have to average up to 0, right? There's only one way to average to 0. I would have to, when I sample my two numbers, I would have to get a 0 the first time and a 0 the second time. That only happens 1 out of 9 times. It's very hard to get a 0 and then another 0 back. That's the only way to get an X bar value to be 0, an average to be 0, is to get 2 zeros in a row. Imagine that your sample consists of 31 numbers. In order to get 0 here, you would have to get 31 zeros in a row out of this bag. And that's highly unlikely. It's the same thing with 4. What's the probability I'd get a 4 for X bar as an average? I would have to get 2 4s in a row. That's the only way to get a 4. Now, if you look at the original one, when I only took one number at a time, the probability of getting a 0 was 1 out of 3 because there's 3 numbers and 0 happens to be one of them. Probability of getting a 4 was 1 out of 3. It's much easier to get a 0 here. And it was much easier to get a 4 here. It happened 1 out of 3 times. But when you start averaging these in your sample, like we did here, averaging 2 at a time, it's much harder to get the extreme numbers 0 and 4. These happen less often, right? The middle, though, still happens 1 and 3 times, right? To get a 2, it's much easier to get a 2. I could get a 2 by getting a 0 and a 4, that averages to 2, or I could get 4 and then a 0, that is to 2, or I could get a 2 and a 2, and that averages to 2. There's more ways to average to 2. It happens 1 in 3 times, not 1 in 9. So the probability of getting a 2 is still 1/3. So the point is, the extreme values become less likely when you're averaging them up, averaging these numbers up. A 0 is less likely as an average than it is as a single value from a population. Now, and again, imagine doing this for 31 numbers. In order to average to 0, I would have to have 31 zeros in a row in the bag. Highly unlikely. But to get 4, I'd have to have 31 4s in a row. Highly unlikely. This is exactly what bell-shaped says. The extremes are highly unlikely. Numbers in the middle are more likely. That's bell-shaped. That's what bell-shaped is. So that's what the theorem says. Once you're above 30, we pretty much know this is going to look bell-shaped. Extremes are going to be highly unlikely. The stuff in the middle is going to be much, much more likely to happen because you're averaging them over 31 numbers. That's what it says. But it says average won't change. If you average these numbers up, still average to what they were before. It's not going to change. The standard deviation will. Of course it will, because everything's getting scrunched towards the middle. Everything is getting closer to the average. Extremes are less likely. The extremes are what cause more variation. So if they're less likely, then there should be less standard deviation. And it is by a factor of a square root of n. Okay. Okay, last thing I'm going to leave you with, and then if anybody has anything they want to go over with questions, we can do that. In your homework, I'll just mention this. Let me pull it up. Oh, I pulled up the wrong section. Hang on. Let me pull up 6.3. Okay, so in the homework, like I mentioned before, we're going to be looking at estimating not only population means, but maybe population standard deviations. So you have to be careful. Like in this problem, let's read through it. This one says um, 3 households in a neighborhood. That's your population. They consist, the number of people in the households are 3 in the first one, 4 in the second, 11 in the last. Now we're going to sample 2 at random from with replacement from the population, and they go ahead and tell us what the possible samples are. So these are the 9 possible samples. Notice that they want you to find the variance instead of the mean. So what they want you to do is find the variance. Like what I did in my example is I found the average of these. So we found the sample mean for each of these, right? What they want you to do is find the sample variance, which is S squared. So if you wanted to do something like this, you could just go to the calculator, go to stat, edit, and let me clear out this list. If you want to know what the sample variance is for 3, which is the first sample, you enter it in. This is your sample, your first sample. You go to stat, calculate, one variable statistics, and then scroll down to your sample mean, your sample standard deviation, and you would square it to get the sample variance. So it's S squared. So 0 squared, it would be 0. So the first one is 0. Next one, so you put 0 here, right? You'd label this as like S squared 0. Next one would be 3, 4. You just go back and you put 3, 4 in. Now I'm going to put it 3 and then a 4. That's what my sample looks like. I'm going to find the sample variance in these 2 numbers. So I'm going to go to stat, calculate one variable statistics, and then I'm going to scroll down to the sample standard deviation. So this is the S's sample, right? Standard deviation is 0.707. Then I'd have to square it to get the variance. And I think when you square that, you get a number that's close to 2. So your sample variance would be 2 for that sample. So you'd label this one as 2. You do that for 311, see what it is. 4-3, the same as 3-4. So we already know this sample variance will be 2. It's the same. The order wouldn't change anything. 4-4 would be 0. If the numbers are the same, the sample variance is 0. You do it for 411. 11-3 will be the same as 311. And then 11-4 will be the same as 411. So you don't have to do it again. And then 11-11 will be 0. There's no variance in those numbers, no sample variance. And what they want you to do is list the probability of getting the different square values, just like we did for X bar. And so I think what's going to happen is there's 3 zeros, right? There's going to be a 0 from this one, a 0 from this one, and a 0 from this one. So that's going to happen 3 out of 9 times. And apparently, I don't know what the other numbers are. 0.5 is probably this one. 3, 4 doesn't vary very much. So I guess the sample variance is actually 0.5 here. That would happen for 3, 4, and 4, 3. So it's happening 2 out of 9. And then the next biggest one is probably 411, and I guess that's 24.5 if you do it on the calculator. 411 and 11.4 would be 24.5 for your sample variance, 2 out of 9 times. And then 32 would be the biggest variance, 3 and 11, right? I guess that's 32. That happens twice, 2 out of 9. And then next thing they want you to do is to compare the population variance, the mean of the sample variances, because we're trying to determine whether this is a good estimator. Can we estimate the population variance using the sample variance? Is it a good estimator? So first, let's look at what the sample variance actually, the population variance actually is. I'm gonna put 3, 4, and 11 into the calculator and see what the population variance is for those 3 numbers from the population. So let's see what that is. 3, 4, and 11. So I'm looking at the entire population now. This is, and I'm going to look at the variance in these numbers, which is coming from the population. So when I go to stat one variable statistics, I'm going to look at the population variance now because it's a population. So it's going to be, this is the population standard deviation. So I would square that number to get the population variance. It's 3.5559 squared. And it's actually 12 and 2/3. I rounded it off. It's actually 12 and 2/3. So let me write this down real quick, and then once I'm done with this, I'll let you go. But the population variance, right, from these three numbers, this is my population, and X is, number of people in a randomly selected house, just like we had before. And then the standard deviation in these numbers, I'm sorry, the variance in these numbers was 12 and 2/3. Okay, now if you're trying to estimate this, now this is the all-knowing perspective. If you're trying to estimate this, you would be sampled 2 at a time with replacement. Only thing you're going to know from your possible samples of size 2, you're going to know the two numbers that you get. And they listed them for us, right? 3.3 would give us 0, right? 3.4, I guess, was 0.5. Those numbers. So you're going to take up all these 9 numbers, just like we had before, and you're going to average them up. And you're going to see whether they average to 12 and 2/3. They average to 12 and 2/3, and S squared is an unbiased estimator. Okay, so you're trying to see whether it averages to this. So just take all these 9 numbers here once you find out what they are, and then average them over 9 and see if you get 12 and 2/3. And if it does, then it's an unbiased estimator. If it doesn't average to 12 and 2/3, then it's a biased estimator. And I think what's going to happen in this case, just so you know, is I do think this one averages to 12 and 2/3. And so you can see the population variance is equal to the mean of the sample variances. That's what's going to happen here. Okay, so you should run through that and check it. That's what happens. And that means the sample variances target the population variances as an average, and therefore sample variances make a good estimator for population variances. That would be the conclusion that you would make. Okay, and so these problems are kind of in the same vein, but next one, notice they want you to, here's your population, 1, 2, 12, but they want you, and here's the possible 9 samples, size 2 with replacement, listed them for you. This time, they want you to estimate the population standard deviation. So first they calculate the population standard deviation here by plugging 1, 2, and 12 into the calculator, and then going to one variable statistics and looking at what sigma is. And it turns out to be 4.967. It's the actual population standard deviation. Now, let's see if we have a good estimator by looking at the sample standard deviations. Is that a good estimator? So then you would put 1, 1 into the calculator and see what the sample standard deviation is. It's going to turn out to be 0. Put 1, 2 in and see what S is for one variable statistics. And apparently what happens is you get 3, 0. No, you get 1, 0. I guess 1, 1 is the only one that's 0. That can't be. Oh, 1/3 of the time. So 1, 1 is going to give you a 0. 2, 2 is going to give you a 0. And 12, 12 is going to give you a 0, which is 3 out of 9 times. And 3 out of 9 reduces to 1/3. So that's where they're getting that from. And then one of them is 0.707. I guess probably the 1, 2 is the next smallest variation. And that happens twice, 1, 2, and 2, 1. So that's 2 out of 9. And then the next biggest is probably going to be 2 to 12, and that'll happen twice, 7.071. Again, the way you're calculating this, you're putting a 2 and a 12 into the L1, and then you're going to one variable statistics and looking at the sample standard deviation, S sub x. And you're going to get 7.071 for 12 and 2, or 2 and 12, both of them. That's why it's 2 out of 9. And then the largest will be from 1 to 12, and apparently that's about 7.7, and that happens, 2 out of 1 out of 112 and 12.1, right? Happens 2 out of 9 times as well. So there's your distribution. And then you're going to add up all these numbers, all 9 of them, average them up, and it averages to like 3.457. Notice that that's not the same as the population standard deviation. So this one's a biased estimator. And so the sample standard deviations do not target the population standard deviation. And so they are biased estimators. The sample standard deviation is a biased estimator. So it's not always unbiased. Okay. So anyway, that's what this homework is going to look like. Each problem is going to take you a bit of work. Here they want you to estimate the sample median, or the population median, by using the sample median. This one, I want you to estimate a population proportion by looking at a sample proportion. So here, the population is 1 to 12, and they want to know what proportion of the numbers is even. Okay, well, the population proportion that are even would be there's 2 are even out of 3, right? That's 2/3 of the time. And these are the possible samples of size 2 you could get when you randomly pick 2 with replacement. And then you're going to look at how many of these are even, what proportion of these are even as a sample from the sample. So the first sample, none of them are even, right? So that would be 0 out of 9. Second one, 2 is even, right? That'd be 1 out of 2. 12 is even, that's 1 out of 2, right? 2 is even, 1 out of 2. This one, both of them are even, so it's 2 out of 2. So this one's going to be a probability, the answer is going to be a 1, right? So you get 0 here, half of them are even, half of them are even, half of them are even, all of them are even here, so you're going to get 2 out of 2, which is a 1, right? This one, 2 and 12, they're both even, so that's another 1. 1/2 are even, right? 2 out of 2, so that's a 1. Both of these are even, 2 out of 2, so that's a 1. And if you go and count up, there's only one of them that's 0. 0 are even here, so there's 1/9 of a chance of that happening. Then 1/2, 1/2, 1/2, 1/2, 1/2. That happened 4 times, so 4 out of 9. And then the probability of getting a 1 for your sample proportion is even, both even, there's a 1. They're both even, there's a 1. They're both even, there's a 1. And then they're both even, there's a 1. There's 4 of them, right? 1, 2, 3, 4. So that's 4 out of 9. So that's your probability distribution for your sample proportions, right? You get 0 1/9 of the time, 1/2 4/9 of the time, and a 1 4/9 of the time. Now, the actual population portion that is even is there's 2 of them that are even out of 3, so it should be 2/3. What you're going to do is add up these 9 numbers that you got here at the bottom. So you're going to add up like 0 and then 1/2, 1/2, 1/2, 1, 1, 1, 1/2, 1, and 1. Add those up and divide by 9 because you're averaging them up over 9 and see what you get. And you're going to end up getting 2/3. And so the proportion of even numbers in the population, which is 2/3, is equal to the mean of the sample proportions, which, if you calculate it, I think would also be 2/3. I'll let you do that, but they end up being the same number. That means the sample proportions target the population proportion of even numbers. I mean, sometimes you get 0, sometimes you get a half, sometimes you get 1. The actual answer is 2/3. On average, these are averaging to 2/3. That's why they target, right? That's why they use the word target. They target the correct answer. And so the sample proportions make good estimators for population proportion. Okay, so that's that one. This one is exactly what I did, the example I did. The only difference is population now consists of 4 numbers. And you randomly select 2 of them. And then you're going to list all the possible, now there are going to be 16 possible samples of size 2. Then you go through and you calculate the probability of getting any of these sample means. Okay, so I'll let you do that. It's just a little bit longer because you have 16 samples instead of 9, and that's because you have 4 members of the population, 4 numbers in the population, and you're sampling 2. So you're going to get a bigger number of X bar values here. So that's kind of like what I did. It's just a little bit longer. And then I'll let you look at the last one. It's just a summary of all the different estimators that we have. Okay, I just wanted to make sure I looked at some of those because I know that sometimes people run into those other examples. I didn't necessarily go through them, but I just kind of wanted to give you an idea of what's going to happen with those. Okay. Okay, so I guess we'll leave it there. Does anybody have any questions about anything before we end it? Okay. Again, the test is going to be, it's not going to be due Friday like the calendar says. I'm going to extend that till next week. I'll send an email out about that just to remind you. And so at this point, hopefully you should be able to work through all the homework in chapter 5 and 6.3. But if you run into any problems on anything, just email me and let me know. Okay. Okay, and then tomorrow we'll go over 6.4 and maybe 6.5. Hopefully we'll get pretty close to ending chapter 6, and then you can finish the homework and then begin looking at maybe that second practice test. Okay. Okay, let's end it there. And again, if you have any problems, just email me. Okay. All right. Have a good day. Are you, I'm going to stop the recording, and if anybody wants any more help, I can help them. Okay.